Seven, we continue our discussion on expander graphs. But most of today's this one will be, we'll see some applications of expander graphs to various computer science topics. But let's quickly recall from last time, we were talking about expansion. We had defined two notions of expansion. One was spectral. Spectral expansion. We defined a graph to be an ND lambda expander. You recall what this thing, I don't know. It's a graph on n vertex. So it's an n vertex deregular graph such that lambda, the max of lambda 2 of G, actually not of G, but of the walk associated with, so actually strictly speaking, A by N. And lambda n of A by N is at most lambda. That was spectral expansion. And we had also defined vertex expanders. Where a graph is a KA expander. So K is some number between 1 and the number of vertices, and A is a real number greater than 1. This says that for all S subsets of the vertices of G, the neighborhood of S is of size at least A times S. Basically, we have a graph like this, G, except yes. Look at its neighborhood. The NFS, these are all everything to which there's an edge. Set of all V in B is that there exists a U in S, the UV that's connected. And last time we had stated without proof the following fact, that spectral expansion implies vertex expansion. Precisely, we said that if G is a ND lambda spectral expander, then for all rho in 0, 1, G is a all sets of size up to rho n are going to expand by a factor which is rho lambda square 1 minus rho plus vertex. The quality of the expansion, of course, decreases as the set becomes larger and larger. So this is a number always larger than 1 because the denominator is a number between 0 and 1. So it's a number always larger than 1. And the quality of the expansion, as rho becomes closer and closer to 1, this number is getting closer and closer to 1. The expansion factor is decreasing. But for every set of size smaller than n, there is a expansion factor. Okay. Let's try to prove this. We have all the machinery for us to prove this. The proof is just going to be an application of the expander mixing. Which, if you recall, just says for all fg, which are functions on the vertices. If you look at fwg, that's the probability of an edge between fu versus gv, where an edge minus mu f, mu g is less than lambda. Sorry, just sigma f, sigma g. That was EML. What's okay? So it's just going to be, now that I've told you it's going to be an application for EML. What is the f and what is the g that you want to? What do you want to set f to be? What do you want to set g to be in order to do this? So I want to show that every set of size rho m. So S is some set. Let S be some set of size. Let S be a subset of n. The vertices and size of S says alpha n, which is less than or equal to rho n. What do you want to set f to be? What do you want to set g to be? Yeah, that's one thing we could do. Where the proof works out, I'll do something slit which will make the proof even more cleaner. I'm going to set f to be, let us set f to be equal to the indicator of S, and let us set g to be the indicator of t, where t is not the neighborhood, but everything outside the neighborhood. Why is that? So that then this quantity, this particular quantity which we are looking at, what will it be for this f and g? It's the number of edges between, it's a fraction, it's the sort of the probability of a random edge being in S, at one point in S and one point in T. It is 0. It's going to be 0. So for since the neighborhood of S intersection T is empty, we have f wg pi is 0. So the whole thing is just mu f, mu g, lambda, sigma f, sigma g. So we just have, and let's say n of s and say size of n of s is beta n. We want to put a lower bound on beta. That's the proof. So now, what is mu f? Mu f is alpha. It's a density of the function f. What is mu g? It's a density of t, 1 minus beta. What is sigma square f? The standard deviation of the indicator random variable, whether you are in the set yes or not. What will that be? P square is an upper bound. So you notice that this is just expected value of f square minus expected value of which is the right amount. F whole square, that's exactly variance. What is that? Notice because it's an indicator and a variable, expected value of f and f square are the same. Yeah. So this is alpha minus alpha square, which is alpha into 1 minus alpha. And similarly, sigma g square will be it will be 1 beta into 1 minus beta. Rather 1 minus beta into beta, which is the same as beta into 1 minus beta. Let's just write EML. EML tells us mu f, mu g is less than lambda sigma f sigma g. This is just alpha into 1 minus beta is less than lambda into square root of alpha into 1 minus alpha beta into 1 minus beta. So this is just alpha into 1 minus beta is less than lambda square 1 minus alpha into beta. So this is true if and only if beta. So I'm going to collect all the terms of beta. So beta is an alpha beta, take it there. So this is says beta is greater than or equal to alpha by lambda square 1 minus alpha plus alpha. Which is, this is exactly like this, greater than alpha by lambda square 1 minus rho plus rho. Since alpha is less than or equal to. So if you have a set of size alpha, then the neighborhood which is of set of size beta is at least fact. It's an extremely trivial application of the expander mixing. Is the proof okay? So one corollary we saw of this, immediate corollary is G is a ND lambda spectral expander for some lambda. It could be any lambda in 0, 1. Then all sets up to, in fact, every set will expand ng 1 by 2 plus alpha for some alpha greater than 0. What about the converse? Do you expect the converse to be also true? If a graph is a vertex expander, do you expect it to be a spectral expander? Say it's an n by 4 comma 1.2 expander, vertex expander. That is, all sets of size at least n by 4 expand. All sets of size at most n by 4 expand. Notice this one gives a very strong property. It gives every set expands. It's not just sets of a particular size. The quality of expansion keeps deteriorating as the size becomes larger. But vertex expanders, you're only guaranteeing sets of up to a particular size. There's no guarantee on sets of larger size. So in particular, you could have taken separate, you could have taken a graph connected of 3 expander graphs, same copies. Each one of them will expand within it. So if you take sizes which are less than n-third, 1/3, anything will expand up to 1/3 because it will be contained only in one part, or it will be distributed across part and they will all expand. So in particular, if you want the other direction, you do want expansion. You want it to certainly not be, you don't want expansion just up to some factor, at least n by 2. Every set of size at least n by 2 should, at most n by 2 should expand. Then you could expect, only then can you even expect a converse. Is it clear? Because otherwise the graph could be disconnected. I can give you several spectral expanders, disconnected spectral expanders. They will all expand up to their size. And that's fine. But the lambda for the combined, This one is actually 1. It's not, the lambda is 1. It's not bounded away from 1. And the converse is also true. We won't prove the converse. For converse, we require vertex expansion of sets of size.
Even both these things somehow should have followed from Cheever.
Both directions will follow from Cheever. So
because Cheever was exactly
so there's a difference between Cheever and this. One difference is Cheever is talking about edge expansion. It's talking about the number of edges that leave. It's not talking about the neighborhood.
The conductance was defined on the
Base of edges. And Cheever only depended on the second eigenvalue. Whereas vertex expansion will depend on both the second as well as the last eigenvalue. So that's why if you notice it, this proof, somehow lambda square sort of enters the picture. So that sort of makes, even if there was a large negative eigenvalue, it would have pushed it forward. So for the graph G square, this is sort of like a graph G square going on over here, which has all positive eigenvalues and this one. So almost the same proof goes, but I do not know if you can prove it exactly from that. So the proof is verbatim, more or less the same way. So for converse, we require vertex expansion. And in fact, this is the converse theorem. That is, if for all alpha in 0, 1, there exists a lambda in 0, 1. Sorry, for all alpha and for all d greater than or equal to 3, there exists a lambda in 0, 1 such that G is a n by 2, 1. This need not be 0, 1. It can be anything. This has to just be 0 to infinity. Any number. So 1 plus alpha vertex expander. Then G is a ND spectral expander. G is orbit. I'm already saying G is deregular. This is not. And the proof of this, just like this proof was exactly like the easy direction of Cheever. You just instantiated it with the characteristic vector and got it. That was the easy direction of Cheever. The other proof, the proof of this is going to be similar to the hard direction of Cheever. I rarely have seen this proof is due to Noga alone. Rarely have seen lecture notes carrying it. There is a course which I taught in 2008. That lecture notes has this. I have not seen other places which contain the proof of this. If you want, you can look up that proof, but it's more or less along the lines of Cheever. Okay. What we'll do from now onwards. Huh? Which one?
That the proof will require vertex expansion of sets of size.
Of most. That's of all sets of
All
size.
sets of size.
Now, so far we have seen expander graphs. This one I mentioned. What we'll now see is we'll see some amazing applications of expander graphs. I did 2 of them in lecture today. In fact, all the rest of the lecture will be focused on. First, we'll see the first application will be to de-randomization.
So just to if you're if you are in a connected graph which is not bipartite, then right now edge expansion, vertex expansion, spectral expansion are essentially the same. Like we get anything from anything.
Yeah, we will. things will deteriorate, but you'll get one from the other.
Qualitatively,
yes. So if all I'm claiming is vertex expansion, but if you have vertex expansion, certainly you'll have edge expansion. Because you have so many neighbors, then you have to have edges all going out. So vertex expansion implies edge expansion is clear. Edge expansion implies vertex expansion is not clear because it only tells you the number of edges. It doesn't tell you about the number of neighbors. The edges could be going to the same object. So that will not. But if you knew furthermore that the edge expansion, you have both the edge. If you go via Cheeger, then it will tell you the whole proof. Via Cheeger, and you know that the graph is not bipartite. Okay. Well, one of the applications of expander graph is going to be, and here, when I'm going to be talking about applications of expander graph, it's not just the fact that these graphs exist. We will hack the fact that we can actually explicitly construct this graph. In fact, a fully explicit construction. We saw 3 examples last time of construction. We saw the Margulis construction, which was fully explicit. We saw these one that was based on 3/16 Selberg's theorem, which was just a prime cycle with just 3 regular. Then we saw the Lubotsky-Phillips Sarna. The Lubotsky-Phillips and Margulis was fully explicit. The middle one was not a fully explicit construction. Next lecture, we'll see yet another construction, which we'll see with proof that it is actually an expander. We'll see the zigzag expanded construction. But the explications now will actually take certain. We will see the application of fully explicit expander constructions towards 2 topics. One is de-randomization, other is error correcting. In fact, we will be requiring fully explicit, and you'll see why we require fully explicit. So let's do a sort of a detour before we go to the application. Let's just do a detour of randomized algorithms. I'm going to give a very, very bird's eye view of what are randomized. So all of you, have you seen examples of randomized algorithms? So which ones have you seen? Which randomness algorithm? Okay, Barber algorithm for min-cut. Anything else? Huh? Have you seen primality, checking if a number is prime or not? There's a deterministic, of course. There's the Agarwal-Kayal there's always Russell, there is Miller-Robin. There are these. So let's actually look at that algorithm. So how do those algorithms? So let's check how does the primality algorithm. And I'm talking about either Solovay-Strassen or the Miller-Robin. I'm not going to go into details of the algorithm, but how do the algorithms look like? There is this algorithm A, to which you feed the number n or the input x. It tosses a few coins in addition to the actual input. So it has this. So the actual input, let's call the input to be x. It tosses some more inputs called r, and based on this, it says yes or no. It either accepts the problem or rejects the problem. And let's for now look at just one-sided. The reason I gave primality is a one-sided error algorithm. These have the feature that say this is x or n. So if n is prime, then the probability over the random coins that AXR accepts is 1. It always accepts. Whenever it's a prime, these algorithms seem to always accept. When n was composite, probability over R, A XR, in this case, you wanted to reject. The rejection probability did not happen all the time. It happened, say, only with probability half. This was a feature of both the Miller-Rabin and the Soloway-Strassen algorithm. If you have seen the algorithm, in one case, these are one-sided error algorithms. You can also talk about two-sided error algorithms. But for this, like today's lecture, we will not talk about two-sided error. There's a problem in the first problem set which will handle two-sided error. By the way, the first problem set is out. So it's went out last night, put it online last night. You have 2 weeks for it. So today is the 13th, 27th is the deadline. As I mentioned, there are four problem sets, and you will be graded on the best 3 of the 4. Okay, so that's a one-sided error algorithm. And you can state it more generally, that is, if X is in the language, then this is for primality. More generally, if you have just some arbitrary language, this is probability R, A XR accepts is 1, X does not. Probability R, A XR rejects is greater than or equal to half. These are, I believe, what are called co-RP algorithm. I think I messed it. I should have done it the other way around. I should have called composites. These are co-RP algorithms. The name is irrelevant. You will learn this if you're doing the complexity course. Prasad will define these classes. Okay. What we're interested in now, of course, there's a randomized algorithm. Just like in the primality case, we first had randomized algorithm came a good 30 years before the deterministic algorithm of Agarwal-Kayal. Now, when you want to ask, is randomness really required? Can you reduce the number of randomness? Can you remove randomness completely? So sometimes you might be unhappy with 50% error. You don't want an algorithm that makes 50% error. You want an algorithm that's right all the time. So how do you reduce the error of this algorithm? You just repeat the algorithm 3 times. So you can think of question I want to ask now is, can one reduce the error for a randomized algorithm? One obvious way of reducing the error is just repeat it 3 times. Say, so that's what I'm going to ask. And one solution is just repeat, say, t times. So AT is the algorithm which picks random points R1, R2, RT. First step. Second step runs. So this is AT is so on input X runs AXR1, AXR2, RT. It runs it on all the T different versions. And when should it accept? Suppose X was actually in the language, every time it will say accept each of these. If X is not in the language, with probability half, it's going to say reject. So even if one of them say reject, you surely know it has to be reject. So you accept only if all the runs accept, and otherwise you reject. So basically, 3 is this algorithm accepts if and only if all the T runs accept. Is that fine? Now, what's the error of the algorithm? In the S case, so let's ask this. Let's ask. Suppose X belongs to the language. What's the probability over R1, R2, RT that AT errs on X? Will it ever give the wrong answer in this case? I'm assuming one-sided error this way. That is, will it ever error here? So I have an algorithm which, if the string is in the language, will accept with probability 1. Now I'm running at t, and if string is not in the language, it will err with probability at most half. So what is the probability this will err? Will this err at all? Every one of them will accept. Every one of them will accept. So this is going to accept with probability 1. But the interesting case is the other one. X doesn't belong to the language. What is the probability over the random choice R1 to RT that AT errs on X? It makes a mistake. So for each one, it makes a mistake with probability half.
That means 0. 80 error.
Oh, sorry, you're right. It is correct all the time, so the error is 0. What is the probability in this case that it errs? All of, and what's the probability that happens? 1 over 2 to the t. So this is less than or equal to 1 over 2 to the t. So you have made the, and let's call this number, let's define this number to be delta. So we have this error reduction technique. We have reduced the error from half to delta, and delta being something like 1 over 2 to the t. By how much? And the process was repeating t, which is which is exactly log 2 to the base 1 over delta times. Okay. So if the original number of random coins was R, how many random coins are you using now? So number of random coins of AT or is, let's call it A with error del, or let's call it AT only, is equal to T times number of random coins of E. It's increasing by a multiplicative factor of T. What we will now see, we will actually use expander graphs to show that we can get the same error reduction without such a huge, that is, you don't have to pump in so many new random points. You can pump far fewer random points and yet get such a dramatic error reduction. In fact, the first application, we will not pump in any new random points, but yet we'll reduce the error from half to some very low number. Then we'll see another one in which we will reduce it even further, but there we'll pump in a few random points. So, want to say expander graph. Give you an error reduction with a much lower number of additional random. And we're going to do it. I don't know, have any of you seen these things before? If you haven't seen this, is actually a stunning application of expander graph. What we'll do is, so let's look at the space of random coins used by the algorithm A. Let's say that is, it is R coins it uses. That is, the string R belongs to 0, 1 to the R. So you have this sort of a, that's the space, 0, 1 to the R. And for a, that's the, you're picking points from here at random and running the algorithm. For each particular X, so if X is in the language, so for each particular X, for each X in the language, for each X, not necessarily in the language, let bad of X with respect to the algorithm A be the set of all those random coins R in 0, 1 to the R, such that AXR is erroneous. That is in the, if X was in the language, it rejects. If X was not in the language, it will accept. Sorry, that's a capital R. So what do we know? We know if X is in the language, bad AX is empty. There is no bad random string, erroneous random string. If X is not in the language, then bad AX is how many? This is the size of this is less than or equal to half of 2 power R, because at least half the strings are going to are good. At least half, the at most half are bad strings. Okay. So that's the picture we have. And running it t times is just picking the coin. It's just increasing the set of random coins used by the algorithm from 0, 1 to the R to 0, 1 to the RT. What we'll now do is we'll just impose. I'm going to do this. The idea which we're going to use is impose a deregular expander graph G on 0, 1 R. This 3 regular could be 2 regular or something. So 0, 1 R. We're going to think of the vertices of the graph as 0, 1 to the R. Notice this is an exponentially large size set. We are going to just think of some expander graph whose vertices are this. So the edges have no structure right now. Just it's an expander graph. And I'm now going to design this new algorithm, which I will, instead of calling it, it's AT, but it is, should I call it AT? Let's call it A. Let's call it, I'm going to call it AG, L. G is this expander graph. Notice I don't have time to write down this expander graph because I can't, the expander graph is on set of vertices, which is humongous. I can't write 2 power R. But I have a fully explicit construction. You tell me a vertex, I can tell, and another vertex, I can tell you which are its neighbors. So suppose we have this property.
Just for the reason to motivate why we are trying to impose an expander graph on this is because we're in some sense trying to estimate the size of the bad set.
How we are estimating, what we want to do is we want to pick t coins randomly in this one, p random coins. We know that an expander walk will mix to the uniform distribution very fast. So we want to, instead of picking the coins randomly, we want to pick it in a much more less randomness fashion using the expander. So we'll see 2 of 1. What we'll do is on input X, first thing we'll do is we'll pick a random coin. We'll start off with a random point. That is basically we're choosing a random vertex in the graph. And then for all R prime, which is in the ball of R of radius L. So basically, we're going to choose a random R. We are going to walk in the expander for L steps. And for everything in this ball, we will run AX R prime. And accept only if all the runs accept. Okay. Is the algorithm clear?
We fix L before.
L is some parameter which we fix. We will decide. For example, if L were 0, it is just the original algorithm. Because you're taking a random thing and you're just running on it. Nothing. You're not taking any ball of radius 0, which is exactly the original algorithm. Instead of running on what you're running, you're picking a particular vertex and you're picking you're picking a particular random point which you're thinking of as a vertex in the expander graph, and you're running the algorithm not just on that particular vertex, but on all its up to L size, all other random points which are at a distance of at most L away from.
The Hamming distance.
The Hamming distance is at most L, but the Hamming distance is according to the expander graph. It has nothing to do with the original problem A or. Okay, so this is this ball that's important.
However, define the graph. We know the vertex is 0.
The vertex set is 0, 1 to the R, and it's some expander graph. That's all we care about.
We don't know the explicit.
No, I assume I have a fully explicit. That is given a vertex, it's 3 regular. So let's assume fully explicit. I give you a vertex. There's an algorithm which will spit out what are the 3. For example, look at the Margulis construction. I told you XY, the vertex. It will tell me what are all its 9 neighbors. So you know this. So once you give me a vertex, you know its neighbors. Let's assume we know this. And let's assume it's a Margulis expander. Let's further assume it's actually I'm going to assume, I haven't told you which expander graph it is, where G is a n by 2 A expander, vertex expander. For some A greater than 1. Once again, what we want to understand is pad of this, let's call this, okay, AGL for X. Notice this is once again, this is a set of all, what are its randomness? Its randomness is R in 0, 1 to the R. These are the things on which it errs. When will a thing err? You're starting on a particular point. When will this point be a bad point for? So we already know. So I want to say this is a bad point if the ball of around R of radius L is fully contained in bad AX. If that entire ball is contained in the erroneous set of this, only then it is erroneous. Even if one of them goes outside, you're in a good shape. That's the only case. The ball R of L, the entire ball of R of L, and by the way, this is only true for X not in the language. It's actually true for both. The other one, this is empty and hence this will also be empty. So this is a statement that's true for everything. Once again, if X is in the language, there's nothing to be done. Size of bad AGL of X is 0. The whole case, sorry, when X is in the language. the whole case is when X is not in the language. So here we know that bad A of X is of size at most 2 power r by 2. And the question for us is what is bad AGL? How large is this? Now, so we want to compute the size of this quantity. Now, suppose R is, I'm saying not only is R contained in, so how, firstly, is ball of, is a set of this bad AGL, is it of size at most half? Can it be larger than half or smaller than half? It has to be smaller than half because if the
Set.
is the size of the set, is it fractional size larger than half or smaller than half? It has to be smaller than half because that otherwise even the starting point, well, there's actually one starting point which is not in bad AL because bad AL is of fractional size half. I want to say not just that. I take one step from this point that should also be of fraction size half, at most half. So let's look at this. We have this picture. So there is that's bad AX for us. I'm using A. So let's use this. Let's use this. A is this is so this. Let's use this kappa. A is the algorithm.
If the AGL, A sub GL algorithm,
Mm-hmm.
we are running R prime, which is in the ball of R with radius L for all
Yeah.
R prime.
Yes.
That can be also exponentially.
Yeah. Well, okay, so good question. That can be exponentially many. So we don't want that to happen. So how large can L be so that is not exponentially many?
No.
So log, because each time the radius is increasing by a constant. This is where I want it to be a constant degree expand. I want it to be such that. So I will run it for eventually I will run it for L being something like order log n. We will look at that. We'll come to that in a second. But let's first try to understand this part. So this is bad AX. That's the original picture. Now, what should we have? We should have this was the this should be bad AGL of X. It has to be contained in bad age, certainly. I'm claiming not only is it contained, its neighborhood should also be contained. Because otherwise steps of one are the ball goes outside. Not just that, if you even take else times the neighborhood, it is still contained in this. So I want to claim if this is a set yes, define the set yes. I want to claim yes is contained in bad AX. The neighborhood of S is contained in bad AX. The neighborhood of S is contained in bad AX. And so on up to this being then done TL times is also contained in bad AX. Is that clear? They all have to be in bad AX. In fact, not just the neighborhood, it's this n plus of S, which I had defined. That should also be contained. This is also true. But you know that each time, when you from here to here, the size of S is increasing by a factor kappa. From here to here, the size of X is increasing by kappa square. Another kappa. Notice it will increase only if the original set was smaller than half, which it is. So all the way, so you started from a set yes. This set of S is going to be, each of them are in bad X. So each of them increases by a factor kappa. So all I want to claim is NL of S is, since yes, n of s all the way up to n L minus 1 of s, all of them are less than or equal to 1 by half of 2 power r, we have that size of NL of s is at least kappa to the L of size of s. But then we are done, no? What is the probability that R is in bad AGL of X? This is exactly the probability of, this is the size of bad AGL of X divided by 2 power R, which is exactly size of S divided by 2 power R. But this is less than or equal to size of NL of S by kappa L by 2 power R because of the previous inequality. But NL of S is still in bad A of X. So this is still less than or equal to bad A of X by kappa L 2 power R. This we know is half. So notice at the end of this, the original error was half. Now what's the new error? The new error is 1 by 2 per kappa L. So if kappa is some fixed constant, it's like 1.1 or something, we have got it exponentially down in L. So now let's go to Soham's question. So how large can L be? So the main takeaway from all of this, the takeaway is by running A on a ball of size, a ball of radius L, we reduce error from half to exponentially small in minus L. That's what happened. Now I would like to make this very, very small. Can I make L very large? Question. That's the next question. L is, and that was what we answered. We said that L can't be, you still want the algorithm to run in poly time. So for that, let's look at the run. The question now is how large can L be? Let's look at runtime of AGL. This is just the size of the ball RT times the runtime of AG, and this quantity is what? Is at least d plus 1 to the power t to the power, sorry, this is L. That's the quantity, that's the size of the ball. Therefore, you want this to be polynomial. So you choose L. So choose L to be order log n. Order log. Notice now if we had a fully explicit, so by choosing L to be order log n, we reduce error from half to delta, which is exponentially in log n, that is basically 1 over poly n. You can choose the constant before the log as large as you want and make this polynomial as small as you want. Notice we have not spent a single extra random bit to do this. The number of random points is exactly the original number of random points. It is just picking a center without using any additional random points. But by running the algorithm, a polynomial times over. Poly n many times. And this construction exists only because there are explicit construction expanders. Because we have that, we could do. And you need the explicitness. The expander construction can't, because you must be able to write this down on this exponentially large graph. Given our graph vertex, you must be able to tell for its neighbors. So you must be able to do this walk on the expander graph without actually even writing down the whole graph. This is an amazing example of just the fact that you have vertex expanders at X.
We don't know any other way to do this.
Huh?
We don't know any other way to do this.
Of removing all randomness? Yeah, I don't know how to do it. Of course, eventually BBP, SP, none of this is needed, but yeah. But this is more general than that. It is not just for problems in BPP. Anything you can reduce the error. This construction is due to half Pippinger and Simpson. Okay. Questions? What I now want to ask, we're going to ask another one. We want to ask if you can, given that expander graphs can be used, reduce the error from half to 1 over poly. Can we make the error go to even smaller than? Can we make it 1 over inverse exponential? So I'm going to ask. The reason that's preventing this sustain, notice the error can go down. That is, the error can go down from half to kappa to the 1 over kappa to the L. The bottleneck is because the running time increases as d plus 1 to the power L, because we are running it on the whole ball. And the ball is growing exponentially in L. So what we'll instead do is we'll ask for another construction. We'll ask, instead of running it on the whole ball, let's just choose a random walk of length L and ask, and just run it on the things in the random walk. And then ask, will this get it done? So we're going to ask the following. So basically this question comes from, can we reduce error even further? Maintaining poly time, running time. So let's say, instead of running, the idea is going to be run on a random walk of length L instead of ball of radius L. Notice this this has advantages and disadvantages. Advantages, you can we are going to expect the error to still go down exponentially in L. But you can run, for it to go exponentially in L has to be made polynomial. You can take walks of length polynomially long. That is, you're going to run the algorithm only polynomially many times. That's one thing. But you are pumping new random bits because you're taking a walk. So from the first vertex, you have to go to the next vertex, you have to choose one of the neighbors. So you have to toss all log d coins. Log d is a constant. But you have to toss log d and you have to toss this L times. So you are tossing L times log d.
In the previous thing, what property of expander did we use?
Vertex expansion. The fact that any size of set at most half expanded by factor kappa, where kappa is larger than 1. Here we'll actually use the stronger property. We'll use spectral expansion to prove this. So this will actually prove the following theorem due to itai conversion. Am I ready? It's sometimes also referred to as the heating set lemma. So we call it a theorem and a heating set. Just call it heating set lemma. Or random walk on examples. Okay. I'll state it very generally for a random walk, but eventually we'll apply it only for the random walk on a fixed expander graph. So let Huh? Yeah. So AKS did work. These two people worked with each other for quite some time. So they have several papers. This is not the AKS paper. Of course, now the AKS is a different AKS. It's Agrawal Kayal Saxena. But till then, it was a sorting networks paper was AKS. Yeah. So let W be any reversible random walk on the space V with max of lambda 2 and lambda n being at most lambda. So we're going to ask the same property. You have a bad set B in the graph. So the proof is going to be, we have a bad set B in the graph. This is the state space V. There is a bad set B. I'm going to ask and let x0, x1, xl be a random walk. Be the L steps of a random walk. And what do I mean by that? X0 is sampled, it's a uniformly random vertex sampled according to the stationary distribution. In our case, in the expander case, it will be a uniform plus 1, and xi plus 1 will be a random neighbor of a random, it will be a random neighbor of xi given by the random walk W for I less than L minus, or I from 0 to L minus 1. So that's a random walk. So I'm picking a random walk, which is of this type. I pick x0, I pick a neighbor x1, I pick another neighbor x2, x3, x4, and so on up to xl minus 1. That should make it L minus 1. So that is exactly L steps. And B is some subset of V such that the density of B is mu. What we're going to ask then, what is the probability that all the xi's lie in B. That is the random, this is the probability you will get accepted. Every single step happens to be an erroneous thing. This is over the choice of x naught all the way up to xl minus 1. Are you going from 0 to l minus 1? We will show that this is at most mu into lambda 1 minus mu plus mu the whole power n minus 1. So let's stare at this a little bit. Let's suppose it was not, suppose we are picking them independently. That means we have the complete graph. That means lambda is 0. Then it is mu times mu power L minus 1, which is mu power L, which is exactly correct. If you're going to pick L things independently, what's the probability that all the L will fall in the set B? Each time you have to probability mu. So this is that. This is stating that it's almost like that, except that the first step is with probability mu. That's clear. This is why x naught. It says the next steps, even though they are not independent steps, they are not going down like mu to the power L minus 1. It's going down by a slightly larger number, but still some number less than 1. Once again, notice this is a number less than 1 because this is a convex combination of mu and 1 minus mu. So it's a convex combination of lambda and 1, which is a number less than 1 because lambda is. Okay, so this is the hitting set. Is the statement clear? It's a longish statement and I stated it a bit, all it's this one, but it should be a very, it's a clean statement. It's a very clean statement. Is it clear? Statement clear? It's saying there's a bad set. I'm asking, notice this is a good walk because this walk is leaving the set B. We are asking what is the probability that the walk is fully contained in the set B. And that probability is more or less as if you are picking it independently. Notice this is remarkable in terms of randomness. Randomness, previously to run the algorithm L times, you needed to multiply the random points by L. Here to multiply the algorithm by L times, you need only order L extra random bits. It's an additive order L. It's not a multiplicative order L. So you're improving the number of random points running to reduce the error from half to exponential in L with just an additive random L random points, not with a multiplicative random L point. And this can be done for any randomized algorithm. Any randomized algorithm, you can reduce the error exponentially in L by just with an pumping an additive L random points. And why is it additive L? You require to take L steps. Each one requires log D bits of randomness, and therefore it is order exact the number of additional random points is L log D. The comment on the remark on de-randomization is just the following. We can then jump to the proof of it. So it's error reduction. From half to exponential in minus L using additional L log D random points. Instead of a multiplicative L. By the way, you can also ask if the corresponding Chernoff bound is true. That is, if you had picked it independently, this one, what fraction of the walk will you see in the set B? A mu fraction. If you picked independently, a mu fraction. You can ask what fraction of the walk actually goes through the set B. You can show that that's also almost mu. This is actually a problem in the problem set. You use the hitting set lemma, and using this, you'll convert it to the Chernoff. This is actually problem 5 in the first problem set. Okay, that's proof of the hitting set lemma. Question on the statement of the hitting set lemma. We want to do, we want to ask the probability, we want to bound this probability. So let's call it. Let's for now let's define this probability to be Q. Define it to be this, which is probability that and of xi belongs to B. I going from 0 to L minus 1. Let's just write this down fully. We know exactly what it is. What is this? So we're going to take an L step walk. So let's assume the vertices are U0, U1, U2 up to UL minus 1. We want to ask what is the probability that all these vertices are in B. So let's pick. So let's run. This is exactly the summation of picking U0, U1, UL minus 1 and B. The probability that you start with U0. You take a step from U0 to U1. Then you take a step from U1 to U2 and so on. UL minus 2 to UL minus 1. This is exactly the probability that you take this particular thing and you run over all possible such things. Some of them might be 0, but this is exactly this probability. Is that okay? I just opened it out and written it. Now, so the reason I want to do this proof is there are several steps in the proof which are good indicator of how to do these sort of calculation, not just in this context, but in general. So whenever you have the summation over an R, now notice B is a set which we do not know. Typically, when the summation is the whole thing is something we can do. What we'll try to do is we will change the things over here so that this summation actually I can run it on the whole set. So we will insert quantities which will make it 0 when this is B, but when it's in B, it will actually be 0. It will be exactly this quantity. So this is a useful tool. Whenever you have a summation over a thing which you don't know how to handle, you change these things so that this summation is easier to run. So what's one thing? So let's define this matrix because we'll be inspired by, because everything here are matrices in this one. Let's define this matrix P, which is R of V cross V. Matrix P. Think of B, B complement, B, B complement. And in B, I'll put the I, and everywhere else I'll put 0, 0, 0. Think of the vertices, I'm ordering it as B, B complement, and I want to claim Q. Q is exactly summation of U0, U1, U2, UL minus 1 in V. Now I'm going to the whole thing. Pi of U0, P U0, U0. I just want to ensure P U0, U0 will ensure if U was not in B, it will make it 0. Into W U0, U1. I'll put a P U1, U1. That will check that if P was not in B, it will make it 0. A W U1, U2, so on up to a P U2, UL minus 2, UL minus 2, a W UL minus 2, UL minus 1, and then also a P UL minus 1, UL minus 1. Sure. Right? Notice this is the quantity which we know. What is happening here? This is now when I range over this whole set, this is exactly like matrix multiplication. This is, you multiply the matrix P into W into P into W into P into W so many times. And then it looks, so if you forget about this pi u naught, this is exactly like matrix multiplication. And then you're summing up all the things. So you're taking this matrix, multiplying it with the all ones vector, and then just averaging it according to pi. So I want to claim, just staring at this, this is exactly P WP L minus 1, the all ones vector, the all ones vector, the 2 pi. Sorry, why am I typing 2 and it's just a pi? Is this clear? This and that is exactly the same thing. Because this is taking this matrix, long matrix product, and then you're summing up over all things. Therefore, that's multiplying by 1. And then you want to average further. So you're again multiplying by all ones vector and pi. So this is exactly the quantity. So the reason for adding that extra thing is gave you a nice compact way of writing the whole thing. Okay, this is okay. So for questions. Now I want to do something. Basically, now we are going to use Cauchy. It's now rest of the proof is going to be several Cauchy-Schwarz, and somewhere we are going to use this W has bounded eigenvalue.
Can you just repeat why and how are we saying that is W?
So what? Let's look at this. Let's look at PU naught, WU1, U2. Let's look at a particular term here. This is exactly the quantity PU0. What do I want to say?
For a moment, if you forget the PI,
You
drop the PI, then you're following a path U0, U1, U2, U3, blah, 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 in the graph according to the graph. Sorry.
Yeah, so.
And then you have a P in between, which is like that. So it's like geometrically, you can think of it as take the bipartite graph according to W, and you're taking multiple copies of it, and you're putting like a matching type in P in between. And you're looking at paths in the graph that correspond to all the terms.
Or equally, just write down what this is. You will exactly write down this expansion of this. You will get exactly that. Just it take you. These are not easy. This one, but you have to get comfortable with this. And the whole point of introducing the P was when I can go all the way, I can write it so cleanly. This to just get comfortable with this. Step. Write down this expansion. This one, then you see it's exactly that way. I want to use Cauchy-Schwarz. So basically, I'll bound a vector. I'll bound a inner product of two vectors by the size of the two vectors. You want the two vectors to be as small as possible. So it will be the inner product of size of this vector will be at most the norm of this vector times the norm of this vector. Now you can do a little more because notice over here when once I apply P1, the last guy is I'm going to apply a P on the 1. Therefore, I could have also written this to be PWP L minus 1 over the 1 vector over 1b. That is, whether I put 1 or the indicator of 1 or the indicator of b didn't matter over here because the other guys are going to contribute 0 because this will be 0 on those guys. So I'm just going because then when I take Cauchy-Schwarz, the norm of this vector is smaller than the norm of that vector. So it's useful to keep this. So that's it. So as we start, we're now just going to bound this by the norm of this vector. In the 2 pi world times the norm of this vector in the 2 pi world. That's just Cauchy-Schwarz. So let's first understand what is the norm of this vector 1b 2 pi square. This is just 1b in the pi world. So I claim this is just pi of b, which is mu. So this quantity is square root mu. So we are actually now interested in the other quantity. Other quantity, we're going to do one. So let me just this, this is less than or equal to, I can put a square root mu here. And I'm going to, this is a trick and I don't know how to explain this trick all the time, but let's see. I'm going to write this as PWP to the N minus 1. Notice these two are different because there I'm taking P vector and putting WP, 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 WP. Here I'm putting PWP into PWP into PWP. And this happens since this and P square equals P. But whether P square is the same as P somehow makes proof easier. And I remember this change happened while I was in grad school. Previously used P, and that would have caused the square root lambda in the proof. This somehow makes a lambda improvement. But I don't know how to explain off this one. If you get comfortable, when you later see why actually P on both sides is useful. We use the fact that P is a projection function. So it will P square is P. Okay. So now we want to understand. So the goal of now is going to be understanding this quantity. So the rest of the proof is going to be how large is PWP when I apply it to the all ones vector. This is going to be our goal for the rest of the. I think I'm already short. No, I'm not yet short, right? But I will soon shoot. Okay. So we'll actually ask a more general question. The first one we could answer because we knew the first. Notice these are the same. It's the same thing. There are two vectors. We have to bound the norms. The first vector, we knew the vector exactly, so we could write down its norm. The second vector is a vector on which you're going to apply this PW several times over. I don't know how it goes through, but yet we will try. So through this, we will ask the following properties. We'll ask the following one. So given a square matrix, we'll define the norm of the square matrix to be how large, when the matrix hits on a vector, how large it becomes. So it's basically the max over all x, which are not zeros, mx by x. Notice for a square matrix, this is the largest eigenvalue. This is Rayleigh coefficient this is not the Rayleigh coefficient, but it is the largest eigenvalue. Rayleigh coefficient is a square on both sides. It's not the square on both sides. Rayleigh coefficient is x, mx, xx, but this is also the same thing. So this is the largest eigenvalue. I'm going to define this notion. In fact, these are the reasons I'm doing this proof. There are several important notions that we'll use. Various things will happen here. This is where we'll define the norm of a matrix to be how much it scales a vector. And let's make some observations about this definition. I want to ask norm of m to the power, say, r. R was a bad choice. M to the k. If the same matrix is applied k times, this is certainly less than or equal to the norm of m to the power k. Each time you apply it, it's going to expand it by a factor. At most m, at most the spectral norm. Therefore, if you're going to apply the matrix nk times, it's going to be this one. Is this clear? The proof of this? Yeah.
Would it be an equality?
It will be an equality. The way I have defined it, it will only be less than or equal to. If this happens to be, if the vector happens to be the same vector, if it happens to be the eigenvector, then the point is the maximizer for mx, after x, it should be the same x. Then you know that you will have the same thing. It could be,
You are taking, but since it's the eigenvalue anyway,
huh?
it's the eigenvalue.
Yeah. So if you knew it was the largest eigenvalue, then it is an equality, I agree. But my definition will only prove that is less than or equal to. If it was the largest eigenvalue, once you then later on realize as the largest eigenvalue, it's an equality. I will only need this direction, and that only needs that definition. That's all I'm claiming. It's actually an equality. What you're saying is true, but that needs the fact, this whole thing about you having an eigenvalue, eigenvectors, and all of this. I don't even need the notion of an eigenvector for this point, for proving this inequality. What about the norm of two vectors? Sum of two matrices is the same. It's a similar proof. You can show it as norm of M plus norm of M2. And here you should clearly see why this need not be an equality. Let's say the same X is a maximizer for both, then you can see it, but otherwise this will only be an upper bound. So let's keep both of these in mind. So once again, what did we want to bound? We wanted to bound PW PL minus 1 of the all ones. This is a vector we wanted to bound. So we're going to say it's the norm of this matrix times the norm of this quantity. Once again, this quantity you can actually make it 1b because you're at least applying p. So let's just make it 1b. This is the same as, because whether you put 1 or 1b there, it doesn't change. So this is less than or equal to norm of PWP L minus 1, the norm of this into the norm of 1b in the pivot. Is that okay? This we already found. This is less than or equal to norm of PWP L minus 1 into square root mu. Okay. Notice, so it's almost this square root mu and the other square root mu will combine with each other to give you the mu. Let's look at let's recall what did we want to prove. We wanted to prove mu times something to the power L minus 1. We had one square root mu, another square root mu, the mu has been obtained. If we show that this norm of that matrix is just this bounded by this quantity, we will get L minus. We will get a product. So let's finish that, and I might take another 5 minutes. So to complete the proof of lemma. Suffices to prove the following claim. Equal to lambda 1 minus mu plus mu to power n minus 1 square root mu, which is times lambda 1 minus mu. So that is the end of proof of lemma. We have to prove the claim. Let's go. Okay. It'll take me a few minutes to prove the claim. So the way we'll prove the claim is let's do a warm-up case. Let's assume W is not the random walk. W actually picks independently according to the stationary distribution. Let's do a warm-up. W is actually W end. That is, each step is an independent vertex picked according to the random vertex. Picked according to pi. That is, W actually looks like pi. So irrespective of which vertex you are, the next vertex you are picking according to the stationary distribution. So not W, there's a W end. Okay. Let's ask, notice that this is the same as, this is J pi, where J is all ones matrix, and pi, of course, is what we have already seen. It's a diag of the stationary distribution. That's exactly that matrix. This is a rank 1 matrix. For a rank 1 matrix, it's easy to understand its norm. There's only one vector in which it's going to do. All the other vectors, it's going to kill it. A rank 1 vector, there's only one vector which it will do some scaling. Every other vector, it will do this one. So let's actually understand. That's why this is an nice guy. Let's understand. So let's understand this object. Let's want to look at PW ind P. What is this matrix? It's a rank. This will also be a rank 1 matrix. Let's understand which is the one vector it's which going to act on. So I want to claim this vector actually looks like this matrix looks like this. Once again, let's take B complement, B complement. Notice W is a matrix in which every row is pi. P is just identity on B and 0 elsewhere. So what is this going to do? This is just going to put pi restricted to B. Pi restricted to B. Over here it will give, and it's going to give 0, 0, 0. You should just this should be true from the. Now once this is clear, it should be. So then W in P. Let's see what it does to the all ones matrix. All ones are actually all 1, 1B. If you multiply this by 1B, I claim what you're going to get is pi B into 1B. Therefore, this is the rank 1. This is the only vector which is on. This will tell you, hence, since PW in P is rank 1, the norm of PW in P is exactly pi B, which is mu. That's expected. When it was the independent distribution, you're picking everything this one, you should get that one. The proof of the claim should have actually given you mu, which is what it should have given us, and that's what is given you. Is that clear? So this is right. We'll take 2 more minutes. I'll finish. Sorry, I'm taking time, but it's in the midst of the proof. I'll say from here to that one, and this is a very important step that's going to happen when you're looking at these matrices. From here to the other proof, you're going to show it's hardly going to be a change. So I want to look at these two matrices. One is W and W end. W end, I know how to analyze it. That's what happened right here. So let's look at the two matrices. W versus W end. W is an operator, is a matrix operator. What did it do? It took F1, which was the all ones matrix, mapped it to all ones. F2, these are the eigenvalues. I'm talking about eigenvalues. 2, what did it map it to? Lambda 2 times F2. F3 to lambda 3 times F3, and so on. Fn, lambda n times Fn, where Fi's and lambda i's are, let's write it this way, where Fi lambda I, right, are the eigen vector value pairs. That's what W does as a matrix. And this specifies W completely because it's an orthogonal basis, and I'm telling on the orthogonal basis how W is acting. This specifies W. Let's understand what W end does on the same basis. W end maps all ones to all ones. That should be clear. W end was this guy. It's certainly mapping the all ones matrix, all ones vector to all ones. And it's a rank one. That's the only thing it is going to map. Everything else it should be mapping it to. So this is F1, which is this is being mapped to F1. F2 is it's going to map to 0.
There's a mu.
Huh?
Well, all ones is going to be mapped to mu.
No. That is PW end P will get it mapped to PUP. Just W has no B inside it. It's going to map it to all ones to all ones. So all ones is going to all ones. F2 is going to 0. F3 is going to 0. You'll notice that all of these, and these are just because these are orthogonal to the all ones. These all. So this specifies W end completely. So I want to say, because of this, because of writing it this way, I can write hence, and this is one of the most crucial steps of the book. Hence, W can be written as (1 minus lambda times W end plus W error), where W error is a matrix which will send the all ones to lambda times all ones, F2 to 0, F3 to 0. Is that what I want to do?
Lambda F2 to lambda 2.
Yeah, F2 to here. Lambda 2 F2, lambda 3 F3, lambda n Fn. Does it? Why is this useful? Notice what is the norm of WE? It is sending every vector to at most one of these guys. So the norm of it is only the maximum of this. It can never expand a guy there. So, and WE's norm is less than or equal to lambda. This is something, part of this proof you should sort of then. So if a vector has, if W is a vector with eigenvalue lambda, it can be written as 1 minus lambda times just the independent copy, which is doing nothing, plus the error vector whose norm is bounded above. But now we are in good shape. Now let's go back to our proof. We want to bound PW P norm. I'm going to write this as P 1 minus lambda W end plus WE P, the norm of this. This, by what we have seen, this is less than or equal to 1 minus lambda P W end P plus P WE P. The norm of the sum of two matrices is the sum of is at most the sum of the norms of the matrices, and scaling by this one will not do anything. So that's all. This we have already seen. This is 1 minus lambda into mu. The first one, that's quantity. This one, P and P, this is at most norm of P into norm of WE into norm of P. P can at most increase a vector by 1. These are projections. Therefore, it is 1 times lambda times 1. So this is 1 minus lambda mu plus lambda. This is written in a slightly different way. This is the same as
Lambda times.
the same time as, yeah, these two are same. This expression is symmetric in lambda and mu. So it's lambda times 1 minus mu plus mu. That's the end of it. Yeah, that's it. But this main takeaway is a matrix of norm whose second eigenvalue is at most lambda, the second and last smallest number, can be written as an independent copy plus an error whose at most lambda. This is an important thing you need to remember when we're working with matrices. This will come useful various places. And the proof was the proof is extremely clean. Let's stop with this. I want to do error correcting codes also. I'll do it next time.